Start off by giving you a little bit of a primer into the DiffAugment methodology, and then from there we'll go ahead and take a look at we'll take a look at what we can do with it. So what I'm going to do is I'm going to open up the actual MIT lab GitHub repository for data efficient GANs. As you can see on the left over here are some results from GANs that were trained without DiffAugment on the same sort of data set. Versus the ones with DiffAugment. As you can tell, way more photorealistic when we're using DiffAugment. Why is that the case? Well, we know that data augmentation can really help neural networks. Oh, some people are saying there's no sound, so let me know if there is no sound, but I think we are good to go. But as I was saying, as we all know, data augmentation actually helps neural networks a lot because of two things. We get a lot more data, and even with that data, we have different varieties of data, enabling the neural networks to generalize further. And GANs haven't really been leveraging data augmentation all that much because we want to have as realistic of data as possible, because of course the point is to generate realistic images. But with DiffAugment, what they're able to do is they're able to augment the data for the discriminator specifically, the discriminator part of the GAN. And what they can do with that is get neural networks that can run on just hundreds of images instead of having to do thousands or tens of thousands. And it's still able to generate really photorealistic images. And the best part is, the reason it's called DiffAugment, differentiable augment, is because of exactly that. It is differentiable. And so you don't need to pre-process your images and then feed them into the discriminator. You can just call it as part of your neural network, and because it's deterministic and differentiable, PyTorch or whatever else framework you're using can actually differentiate through DiffAugment. So it's really fascinating how this stuff works. Now here's the thing, DiffAugment has currently been implemented in TensorFlow, let's see over here, yep, TensorFlow and PyTorch. So you can see these two different implementations. Right over here is the PyTorch implementation, for example. I have not studied the source code of exactly how this works, but as you can tell, it's not particularly complex. Now in theory, I could just go ahead and rewrite this code in Swift for TensorFlow, but really there's no need to rewrite that code in Swift for TensorFlow. If we can just use the PyTorch version. And so I've been doing a little bit of research as to how exactly PyTorch and Swift handle tensors in the back end. Luckily, they both store their tensors in row major formats. That means that their pointers to the actual locations in memory where the tensors are stored the same way. So if you had two tensors with the same data type and the same shape in Swift for TensorFlow and in PyTorch, and if you were to take those buffers, you would see that those buffers are equivalent bit for bit. So that makes it really a lot more convenient to handle all of this. And so I feel like let's just actually dive right into beginning to implement this this little compatibility layer, and then let's go ahead and see if we can train a simple GAN and then train a simple GAN with DiffAugment and see what the differences are like in the results. So let's take a look. So I'm going to start off by just creating a little directory. Let's just say Swift PyInterop. Let's go into it, and let's just create a simple Python function. Let's just call this maybe PyTorch test.py, right? And within it, I'm going to import torch, and I'm going to create a torch tensor with 5 and 6 within it, so it doesn't really matter what it is right now. And I'm wondering if I could actually print out the type of this, but I don't exactly know the syntax for that, so I'm just going to force PyTorch to assume this is a floating point value. So float would mean 32-bit, double would mean 64-bit. Now if I do print x.pointer, I believe PyTorch should give me an address. No, it doesn't. So let's actually go ahead and see what the syntax is for that. So let's just say I have PyTorch and I want to get a pointer to tensor. So get a raw pointer from tensors. Data pointer, that's the syntax. Okay. So not too bad. I can just put data in front of my pointer. So if I go ahead and run that, we get, well, we got the function back, and if I run it, then we should get the address. Now that address is a 64-bit integer, and so that we can now use that address in order to actually run some operations. Now here's what I'm going to do. I'm just going to write a super simple C wrapper, and that C wrapper function will go to that address, look for two values, and print out those two values. That's just to see if PyTorch is storing the data the way that I think it's storing it. So I'm just going to write test.c, and we just want to include, standard IO. And we're going to have a void function, print2, which will take a long, which is the address. We're going to cast that to a pointer. So this is kind of unsafe, but it doesn't really matter. And then for int I equals 0, I less than 2, I plus plus. I could just manually do this, but there's no need to. And let's see if I remember the string descriptor for a floating point value. So I believe it's %f. Let's see if that's the case. So pointer I, and then we close. So I'm going to use clang to compile, since that's superior to GCC. Okay, so it does compile properly, and it doesn't give me any warnings. So then what I can do is I can say export to a shared library, and let's just for tradition, let's do fast optimizations, and also we want to output to libpytorchtest.so. Okay, so as you can see, we have our shared library exported here, and we should have the function that I just exported, which, where did that go? What did I call that again? Let's see. I call that print2, which is here, yeah. So we see the print2 function. Okay, so really quickly, I'm going to take a quick break. I do see there are a couple of questions. For example, one from Bishwajit. He asks, Tanmay sir, which language is important for data scientists? So what I would say is that it really depends on the tasks that you want to accomplish. Now, for the specific task that I'm trying to accomplish, which is implementing a generative adversarial network, it happens to be that it's a lot simpler to implement these sorts of things in Swift, and generally you can iterate faster. You can use environments like Xcode. It's typed, so it's safer, and because of that, Swift is generally a more convenient environment in which I can code. However, if we were doing something else, like for example, if I wanted to plot out some data, or if I want to do some sort of other numerical computing that wasn't related to machine learning, Swift doesn't have as strong of an ecosystem, so I would say Python is more important in that case. I do see a comment that says C++, and you're right, C++ is important for this sort of stuff, but that's usually so low level that the majority of data scientists never need to really touch that level. Some of them would, for sure, if you're working on like the back end of something like Swift or TensorFlow or Python libraries, you're going to be touching C++ and C. But that's so low level that there really isn't a need to go there in the majority of cases. However, that is definitely how all of these libraries are actually implemented, is using languages like C and C++ because they're so close to the hardware. But as I was saying, now that we've actually got that library, I'm going to go ahead and see if we can import that into the Python code. So for that, we're going to use something called the ctypes library. I'm going to store this in a pointer. Also, yeah, so just to confirm, I see another comment about Python. Yes, Python is definitely sort of the mainstream language right now. In the future, things are going to be changing because Python isn't really meant for machine learning. It was never designed for machine learning technology, but as you can see, there's such a strong community around Python that even in languages like Swift, it's important to make it so that you can call Python code and you can run Python logic within the language. And so that's what we're going to be doing today. We're going to be taking some complex logic that was put together by MIT just a couple of days ago, the DiffAugment technology, and we're going to be calling that from Swift. And this is generic, so it can be extended to any Python functions that PyTorch runs. So as I was saying, now we have to import the ctypes library. And so let's go ahead and do that. So ctypes import shared library. So I'm gonna quickly take a look at some small samples of how you actually load. Okay, there we go. Load library seems simple enough. So we'll store that in lib PyTorch test.so. And I believe that we actually have to define the function input and output types with C types. And so let's actually go ahead and confirm that. So C types load shared library. Okay, I just need to figure out what the syntax is. Okay, so you don't actually call load library, you just call CDLL. So CDLL dynamic linked library, I would assume that means. Okay, so let's just see if we can get this to work. Oh. Okay, cannot open. I believe it needs an absolute path, not. From the last time I used it, I believe C types is strict about that. Okay, yeah, there we go. So I was right. Now that we've got the DLL loaded in, we can actually go ahead and define the functions within it. So C types call C function. Luckily, the input is pretty standard. As I go ahead and do this, I see another question. For object detection, can we use DiffAugment technology? We can, but there isn't really a need to use DiffAugment. So for example, the Turi Create framework by Apple already does data augmentation for object detection, so you could feed in like 10 examples and it trains a near state-of-the-art object detection system because they're taking your objects and they're putting them in different areas. They're warping, they're cutting out, they're changing color schemes, they're doing all these different things. So regular object detection regular data augmentation works really well for object detection. And so there's really not a need to use it for object detection, but you can. There's nothing stopping you from doing it, although this is very specialized to GANs, so I would recommend using it with generative networks. So back to what we were doing with C types. So what we should be able to do is take this library and define a function. So I should be able to define print2, and I should be able to say the argtypes equals and then an array of all the arguments. So that will just be C-long. Let's see if that works. Well, of course, Python's not going to know what C-long is, so we have to do ctypes dot C-long. Okay, let's see. Okay, so it didn't crash, that's good. That means it's at the very least working. And now if I do lib.print2 and I pass it the pointer, in theory we should get 5 and 6 printed out. Nice. Okay, so we are printing out 5 and 6. Isn't that great? Now another thing that I just realized is that we are probably going too far. No, we're not actually. No, so we're printing out 5 and 6. I do not know why it's printing out a 9 at the end. That is a question that we need to answer. If I don't run this, then it doesn't print out the 9. So I'm gonna say it's something to do with this function. It could be that it could be with the loop. Maybe I messed up the indexing in the loop. But just to sort of make sure that's not an issue, I'll go ahead and run that, modify it to hardcode, recompile, then uncomment this line of code and rerun this line of code. Oh, still printing out 9. I do not know why it's printing out 9. See, if we don't run that code, it doesn't print out 9. It could be the way that the C code is. Let's see, did I actually end up recompiling? It's currently 10.16. Yeah, it did recompile. Let's try just creating a small main function. And within the main, oh no, we don't want to do that. Vim is not being cooperative. Okay, there we go. So what I could just do is create a small array, and again, hopefully this is the syntax for doing that in C, and then I could just do long values and feed that into print2 just to debug that little issue. That should produce a runnable binary that only prints 5 and 6. Why? Let's see. So within the PyTorch test, we're just calling... Oh, okay, I see. So the C function is printing out the values itself. It's not returning anything, it's just returning void. But what I'm doing is within Python, I'm printing out that void, even though I don't need to, because the function does the print for me. Now, it prints 5 and 6. Doesn't look like a lot, but that's actually really, really fun because now that proves we can interoperate between PyTorch and C at the very least. Now, if we had like a day for this live stream, what I would have done is actually seen if we can take a GPU pointer and see if we can actually run a CUDA kernel in C with that GPU pointer. But for now, we're going to keep it to CPU just to keep things orders of magnitude simpler. So we are able to successfully get pointers from PyTorch. Now the next issue is, can we take pointers from PyTorch and can we instantiate Swift for TensorFlow tensors using those pointers? So for that, I was taking a look, I was digging around in the Swift API's codebase over here, and I found this little tensor.swift file. It's in the core. It used to be in the Swift repository, now it's in Swift APIs because they're trying to unlink and sort of generalize the Swift language a little bit. But if I go ahead and scroll down really quickly, you will see that there is a part of this where they're actually able to instantiate a tensor with a pointer. And so as you can see, they're getting a pointer, an unsafe buffer pointer to a certain type. And what they're doing is they're actually creating a tensor using that unsafe buffer pointer. And so what I want to do is I want to somehow leverage that initializer, because it is public, in order to be able to feed that PyTorch tensor into Swift without having to make a copy. So if I were to list out the things that we need to do to go from PyTorch to Swift, first thing is get the pointer. Second thing is tell the Python garbage collector, don't worry about this because now I'm in charge of the object lifetime of that pointer. Then pass that pointer over to Swift, and once Swift has it, at that point I don't care about the object lifetime because TensorFlow is handling it for me too. And so that's the theory. That might cause memory leak, I might need to handle it, but I don't believe I need to. So we'll check. Okay, so a really quick question we see, can't we use TensorFlow? Yes, we can use TensorFlow because there is a TensorFlow, TensorFlow sort of code base for DiffAugment. However, PyTorch in general is more intuitive than TensorFlow. I would say the intuition ranking goes TensorFlow being the least intuitive, then PyTorch, then Swift for TensorFlow being the most intuitive. So I want to use the technologies that are as easy to use as possible, but yet are extremely powerful. Technically, if we were using TensorFlow and we were using XLA, we could squeeze out a little bit more performance, but since we're using CPU right now and we're doing a super simple GAN, we don't really care that much about performance. So, and also another thing is the theory that I'm sort of operating with here is that DiffAugment and data augmentation in general helps us, of course, with the generalization of neural networks. But the assumption that I'm operating with is that it also helps us in the sense that we could use the same amount of data and have smaller neural networks and it would still work fine. The reason I'm making that assumption is because I believe that even when we have a smaller neural network, the fact that we have more synthetic data will help that smaller neural network generalize further. And so the hope is that we can use maybe the same amount of data, right, all 60,000 digits within MNIST, but because we're using DiffAugment, we can use a smaller generator and a smaller discriminator, maybe the same discriminator, in order to have a faster GAN. So that's my hope. That's the reason that we're doing this. Let's see if we can actually achieve that goal. But now let's go ahead and do a Swift test. So within Swift, I'm basically just going to implement or import TensorFlow. And I'm also going to be implementing my C code. That C code, well, how exactly would I call C code from Swift is also another thing that we got to think about. And the reason we have to think about that is because we can't just tell Swift that, hey, there's an external function, and don't worry, because that external function exists. You know, within C, you could say extern void print to long, and just like that, C will assume that somewhere there's a function that matches that signature. But you can't really do that in Swift. And so we're gonna have to figure out a different method of getting that done. As far as I can tell right now, though, one way we could do that is by instead exporting the Swift code to a shared library and then calling that from C, because C allows us to be a lot more flexible and low level. But I will still see. Call C shared library from Swift. Okay, let's see. There's probably some sort of way to do it without having to use a bridging header in Xcode. Or without having to use the Swift package manager, because that's a lot of overhead for something super, super simple. Okay, so it looks like we would still probably need to make a module map, which, again, I would prefer not to have to do. But let's see. Hey, even Shopify Mobile has a blog on this. Okay, yeah, it looks like we actually might need to create a Swift package. That's not great. Let's see, defining a module map, the import header, the package description, compiling the code, using it in Swift. Yeah, this is a lot more. This is a lot more overhead than I thought it would be to call C code in Swift. But let's just check it out. Okay, let's see if the Swift C can actually take a module map manually. And let's specifically search for Swift C. Ah. See? I knew you could do that. Okay, that's perfect, actually. Great. So, what that means I can do is I can create a test C module. I can go within it, and I can do a little defs.h file over here, where I can just say there's a void function called print2 that takes a long value. And from there, I should be able to create a small module map file. So module map. And within it, I should be able to just very simply say, here's the name of my module, which is test C, and I have a little header. Then what I should be able to do, Swift test, is just print2, and I'm just going to pass it nothing. This will most likely crash. It's probably undefined behavior, but let's see what it if it at least compiles. So I'm going to tell it to look where we currently are. Oh, yes, I also need to export my path to be root user bin and then the rest of my path, so that we're using the right version of Swift C. Now, it still can't find that function that we needed to find. Could that be because I need to actually link it against PyTorch test. Yeah, no, it's still not finding it. Why don't you just call, okay, so another question, why don't you just call the C code in Python using Python? Why is Swift always necessary? So look, again, we can call C code in Python. That's easy. What we're doing here is different. And also, we don't need to use Python. We could always just use C types. We don't even need to use Python, which is a lot simpler. But the whole point is that we should be able to use a simple language like Swift, something that's easy, something that's intuitive, something that just works for neural networks, even if we already have an existing code base in a complex framework like PyTorch in Python. So that's the entire idea of today's episode. And at the same time, we're going to be using DiffAugment in Swift in order to train a GAN quickly. So let's go ahead and see. Maybe we actually need this comment in the beginning of the module map. No, we actually don't. Never mind. That wouldn't make sense. Yeah, it still looks like Swift is not finding the module. Oh, we need to import it. Okay, so if I go ahead and import it, as long as I actually, yeah. Now, okay, if we run it, it should find the relevant library. It didn't find the relevant library. I know how to fix this, but I'm trying to figure out if we could just do it the simple way. So let's actually just fix it the proper way. So if I make a copy of this in user lib, in theory, this should just work now. Okay, good. So it's a seg fault, but that doesn't matter. It worked. It called the function. That's what matters. Now that we actually have it calling the function, we are free to do basically whatever we want in C, and we can call it from Swift. So what I'm going to do now is I am going to take my test code and I am going to create a little function that basically just gets a small pointer to a bunch of floats, and I just want to see if I can import that pointer into Swift for TensorFlow. So I'm going to cast the pointer to a long value just so we can get the actual address. And let's see if we can go ahead and compile this. So, okay, address of stack memory associated. Okay, that's an issue because we didn't run malloc. We're actually giving it back an address from the stack, and so we don't want that. What we want instead is an address from memory. And so the way we can fix that is by actually calling malloc size of float multiplied by 2 because we want 2 elements, values 0, values 1. Now if we return the actual address, it shouldn't complain. Well, it will technically still complain because I didn't import the right thing, but that shouldn't really matter. Okay, good. So now I can also copy, if I figure out the syntax, good. So I can copy that new library over, and it can, in test C, I can also create a new definition or declaration. Then in my Swift test, in my Swift test, I can actually go ahead and use that. So if I go ahead and get pointer, just to make sure that this works, even though the result of this again is nonsensical, but still, let's just see if this works. Okay, so we do get the correct pointer. Now the question is, can we use that pointer and pass it to TensorFlow? That will be absolutely fascinating. So the way I'm going to fix that, though, is, remember, in Swift, we can't really just convert an address to a pointer because Swift really values safety. So that's also something that we would need to do in C. So address to pointer, and then we can just make it take the address, and we can just return the pointer version of that. And so if I were to do clang should work. I can copy, and I can also do this. So we have another declaration. And then within my Swift test, I can do print address to pointer, and it should print out the actual address. Nice. Okay, so now we have that in pointer form. I can tell Swift to forcefully unwrap that because I know for a fact that it's going to exist. And if I print out the 0th value, we should get 5. Nice. Okay. Now, here's the fun part. Let's see if we can put that into TensorFlow. So let's go ahead and figure out what the syntax of that is. And so we have a pointer, and we want to create a tensor. So we're going to create a TensorFlow. I'm going to tell it what the shape is. Of course, you would need to do that. And I'm going to give it scalars pointer. And if we print out the tensor, in theory, it should all just work. And it doesn't. Shape scalars. Unsafe. Oh, so we need a buffer pointer, not a regular mutable pointer. Okay. So let buffer pointer equals unsafe buffer pointer. And now we just need to see how to cast a regular pointer to buffer pointer in Swift. So let's actually go to the official Apple developer documentation, which is something that we barely use, but let's see. Buffer pointer is what I care about. Okay. So in here, we can see what the initial, okay, so init start count. Okay, so start pointer count 2, and also I would need to update this to look at buffer pointer. And if I run this and run this, nice. Okay, so this is just amazing. It's incredible. So we can take a C pointer and we can pass it over to Swift for TensorFlow and say, treat this as a Swift for, treat this as a tensor. And what's really interesting is I can even modify the shape. So I could say, you know, it's 2, 1, and each element will be in its own array now. And so, see that, it's in its own array. So remember, pointers are just one-dimensional, right? So for high performance, you're not going to have tensors that are like multi-dimensional in terms of pointers to pointers to pointers. That's not how it works. Instead, you would just have a single pointer to a contiguous block of memory that contains all of your data. And so now we can import. Now we just need to take all those little building blocks that we've just built and put them all together into one easy to use package. Definitely easier said than done, but I'm sure it's possible. And so let's go ahead and first of all see if there's a way to convert an address to, no, let's actually not do that, because I feel like the extra C library isn't too bad and it would take way too much time to implement that manually. Okay. Oh yeah, also I just realized I should move my video image so that you can actually see the code a little better. So I'll go ahead and move that over here. Okay, so yeah, now you can actually see the results, and let me show you the results really quickly. So the results over here are that we are seeing the array 5, 6 in Swift, and we are also seeing this other array, which happens to be 5 in its own array, 6 in its own array, even though we are just creating a one-dimensional pointer, and that's because before we, well, when we're casting that pointer to a tensor in Swift, we're actually telling it that, hey, treat this as a shape 2, 1 instead of instead of whatever else it could be. And of course, you could have this shape be whatever you want, right? Swift for TensorFlow is going to handle it for you. Everything's going to be super fun, and there we go. Now it's 1, 2, and so it's really convenient. Now let's go ahead and, as I mentioned, put together the building blocks. And so what I should really just be able to do now is just import Python kit and say torch equals python.import torch and say pytensor is torch.tensor 5, 6, 7, 8, 9 and convert that to float, and let's just see if that's a thing that actually works. Whoops. Okay, so I'm gonna compile, run, nice. Okay, so Python works in Swift. And from there, what we're gonna do is see if we can tie that into Swift now. So address to pointer, instead of get pointer, we're gonna do pyt.data pointer. And I'm going to convert this forcefully to a Swift integer. From there, the rest should really just be the exact same. Now, if I want to get the number of elements in Tensor PyTorch. Now, we could just multiply all the values together, but I feel like there has to be a better way of doing it. There has to be a better way of doing that. Come on. Seriously, you have to do the reduce? Okay, yeah, we gotta do reduce. But that's fine. It's not that bad. So I can convert to an integer np.product of the PyTensor shape. And for that, of course, I would also need to import numpy, which should work. And then from there, I can just pass it the actual sort of shape that we expect. So int should work of pyt.shape. And in theory, this should compile, although I'm pretty sure there's probably something that I've overlooked. Yep. Yeah, we need a comma there. Okay, so tensor shape is its own thing. It's not just an array of integers. So I'm going to go ahead and clear my terminal as you've suggested. And maybe it needs 32-bit integers. No. Okay, so tensor shape really is its own thing. What defines a tensor shape then? What is it a type alias of, or is it really its own thing? Tensor shape can be initialized. Oh, so we actually have to cast to a tensor shape. But we can use 64-bit integers, so that's nice. Okay, so now if we run, oh my god, that is incredible. That really is incredible. Okay, so what we just did was we took a PyTorch tensor, we got a pointer to it, and we passed that pointer to Swift. And we had Swift for TensorFlow take that pointer as its own. Truly quite incredible. So what I feel like there are two ways now that we could continue here. One is the better way, which is to tell the Python garbage collector explicitly, don't worry about this tensor or don't worry about this object, don't collect the garbage, because I mean, really, we don't want Python collecting that garbage because we want that pointer. But the easier way to go about it would be to just create a class within Swift that actually contains a reference to the PyTorch tensor. Because as long as Swift contains a reference to that tensor, it's not going to let the Python garbage collector collect it. So I feel like I'm going to do that, just because it's easier. So we're going to create a PyTorch tensor, and it's going to be a generic type, so it's going to have a scalar. And what that's going to let us do is make it so that things are a bit more dynamic. I noticed that you have not signed in any of the websites. What websites? Oh, yeah, like GitHub. Well, I could sign in, but there's no need to right now. But yeah, this is going to be a generic. You can use generics with classes, right? I'm sure you can, but it's still something that I just want to confirm. Yeah, you can use generic classes. There's no way you can't. Okay, good. I was just a little confused there. But yeah, so we have a PyTorch tensor, and what we're basically going to do is have a private let pyref, which is just going to be a Python object, and then tensor, which will be this, and let's actually convert that to a constant. And then we also want, what other information would we need? I don't think we really need any other information. Now what I'm just wondering is, never mind, we don't need to do that. So then when we initialize with a PyTorch tensor, it should be simple enough to do the conversion. So we can just do self.pyref equals PyTorch tensor. So now that will not die. Okay, so we can be sure of that. One thing that I might want to do just in case is actually do like a dinit, and then if we're actually deinitializing, free the pointer. But I don't feel like that should be necessary. So let's not do that right now. So we have the reference to the Python thing over here, the Python object. Now we actually have to convert it to a tensor. And so let's go ahead and calculate the number of elements first of all, or first of all, let's go ahead and get the shape. So the shape is going to be the PyTorch tensor dot shape. Then the number of elements will be equal to shape dot reduce 1 multiply. Then we will do the pointer is address to pointer. Oh, but then how do we make that generic though? Come on, Swift has to have a way of converting an address to a pointer. Let's see. Convert address to pointer Swift. So this is the thing about Swift. It's super safe, but it's sometimes that safety can be a little bit annoying. What I could do is manually allocate the memory for a pointer, and then within that I could manually move to the offset where the address is located, store the address, then take that pointer and use that individually. But do we want to do it that way though? Let's see how unsafe mutable pointer is represented within Swift. So let's go to GitHub, and I'm going to go to Apple Swift. Also, the reason I'm not using Xcode is because I'm actually not doing this on my Mac. This is on a separate Linux machine that supports the latest version of Swift for TensorFlow. And so, because this is on a Linux machine, we can't really run Xcode. But regardless, as I was saying, we want to see how they're implementing unsafe mutable pointers, so, or even just unsafe pointer. Okay. We don't want to take a look at tests. We want to take a look at actual code. So let's go ahead and narrow our search down to Swift code only. These are still just a bunch of tests. Okay, now we're in the standard library. So string bridge, string storage bridge. Okay, now we're starting to get some stuff in there. So this is the source code for the with unsaved pointer function, which is really interesting. I've never seen that source code before, but I'm going to open that up just in case that has any useful hints. Reflection mirror. No, we don't want mirroring. We might care about mirroring, but not right now. We don't really care about the Objective-C bridges right now. Array casting, again, don't really care about that yet. Static string protocol, C types. Okay, let's also take a look at that. I feel like that might have some interesting hints. Okay, so let's go ahead and pause searching for a second and actually take a look at this source code. So there's this thing called fixed lifetime, which might be interesting in a bit, but interesting. So now this is actually forcing arc to not free a pointer or free something before a certain time, which is really interesting. But regardless, let's see. Now we cannot call anything with the built-in prefix. Swift wouldn't let you call any built-in functions. So we have with unsafe pointer. Okay, so yeah, that didn't really have any useful information. Let's see if C types has anything. If not, then I'll actually specify my searches for struct unsafe pointer, and that way we can get to the definition of the pointer. Yeah, okay, so that's not going to work. Well, one thing that I could do is I could actually take the C code and I could make it return a void pointer, so a raw pointer, and then I could bind that memory in Swift to the generic type that was passed. Let's just do it that way, actually. So address to pointer is going to return a raw pointer now, which then needs to be binded to the generic type. So let's go ahead and figure out how to do that. So we want to bind an unsafe mutable raw pointer in Swift. Okay, so if we scroll down a bit, we can see that you can do a raw pointer dot load. Nice, that's exactly what we need. Okay, so what we can do is, okay, so what I can do now is I could pretty much just do PyTorch or int PyTorch tensor dot data pointer, and then do dot load as scalar dot type. So that should help us keep it generic, or scalar dot self. That should help us keep it generic. Nice, okay. So now that we've got that, it should pretty much just be as simple as converting to a buffer pointer, which should be unsafe buffer pointer, start being the pointer, count being the number of elements that we have, and then tensor equals tensor float shape, tensor shape, scalars, being the buffer pointer. And then what I can do is just sort of generalize that a bit further. What I can also do is move these things up here. Now, let's go ahead and see if this code compiles, which I will be very happy if it compiles on the first try. No, it doesn't. Okay, let's see. So one thing is that we do want to implement a generic constraint so that this conforms to TensorFlow scalar. We need to camel case pyref. And we need to forcefully unwrap the pointer. Oh, okay, so we need to forcefully unwrap it before we load it. That makes sense. Okay. Now, we need to actually change the C library to return a void pointer. Okay, and we can also erase all these unnecessary lines of code. And also remove them from within my definitions and change the return type, which will necessitate me recompiling and copying the library over. But from that point on, I should just be able to compile. Obviously, I can't do that just yet, though. So, line 18, we have an issue with this pointer. Why exactly? Cannot convert value of type scalar. Oh, so when you load it, it's actually loading it as an element, but we don't want that. We want to bind it to a certain kind of memory. I could just load it and then get another pointer to it, but there's no point doing that. And plus it might be in a register anyway at that point, so let's not do that. So how do we bind an unsaved mutable raw pointer? Okay. It's literally called bind memory. That's good. Does it return a buffer? No, it returns a regular pointer. Okay. So bind memory to, and let's see if there's an example of using this. Yeah, okay, and then the capacity would be elements. Cannot assign value of tensor. Oh, we need to tell the tensor that it's generic. Okay, okay, it looks like things are happening. Now, if we do PyTorch tensor and just pass this and print out pyt.tensor, if everything worked the way it needs to work, we should see 5, 6, 7, 8, 9 printed out without a PyTorch binding. Well, looks like we need to specify the generic type, but when I run it, ooh, it crashed. Let's see where that was. So it crashed on this line. Of course, this is the most error-prone line there is in this entire program. But let's see how we can fix that. So I actually do not immediately off the top of my mind know why that would crash. I feel like it might have to do with the binding memory, because I don't really see how else that could be an issue. Let's go ahead and split this up into multiple lines. So let's say this is the raw pointer, then we'll create a pointer which is raw pointer dot bind memory and whatever else. And let's see where that crashes now. Okay, so now it's still crashing on line 17, so it actually isn't an error with binding memory. Let's go ahead and get the PyTorch pointer. Oh. We have to actually call the function to get the pointer in the first place. Nice. Okay. See, that is exciting. So now we can just implicitly go from PyTorch tensor to Swift tensor in this much code. That is pretty incredible. And it's a pretty transparent conversion too, right? There's no memory copying because we're just using pointers in between. And so what that means is with very, very little memory overhead, or with very, very little CPU overhead even, you could go to PyTorch, call a PyTorch function, come all the way back to Swift, and it just works. Now here's what I'm thinking would be super fascinating. If I could get this to actually be differentiable. For that, though, we would need to go the other way around too. We would need to be able to convert a Swift tensor into a PyTorch tensor. And it looks like we're on schedule too, because I think this will take like, I don't know, 10 more minutes, and then we can actually get to the GAN part of this whole party. And so let's quickly do that. Now, if we're converting a Swift for TensorFlow, tensor into a PyTorch tensor, I could probably just do that in a closure, because we wouldn't, no, actually I would need to do it outside of the, no, I could actually do it within the closure. And the reason I would want to do that is because if I can do it within a closure, then I can ensure the lifetime of the object is long enough for Python to be done its processing before we need to continue. Now the discussion turns to how do you get a pointer from Swift? Because this sort of stuff, unlike Python, isn't very well documented yet because the community is so new. And so let's go ahead and see what we can do with that. So for that, though, I will actually load up the Swift APIs repository. So within sources, TensorFlow, core, we are looking for most likely tensor.swift, but I don't exactly know. So let's see. I just hope there's a, oh no, there actually isn't. I'm just re-going, I'm just going up and down in the find for the Chrome. But what I want to do is figure out a way. Okay, so we need to get the tensor handle first. I wonder if that's public. Can I even access that handle? Because unlike Python, you could just make it private, and I could no longer access, and I would need to recompile this myself if I wanted to do that. I hope that's not the case. Yes, it's public. Phew. Okay, so tensor handle. Now, where do they define tensor handle? Because I could probably get a pointer from the tensor handle. So, oh, this is where it's being defined. Okay, this was TFE tensor handle. This is where we're actually defining the real tensor handle. So, how do we get a pointer from a tensor handle? I wonder. I would probably need to take a look at the actual C tensor type for that, I think. Yeah, let's look at C tensor if that's even a thing. Oh, but C tensor is part of the TensorFlow C API. So let's go ahead and see if we can if we can find out where that's even located, because that's going to be difficult to figure out. We would need to go to the official TensorFlow repository, which is a mess. There's so much stuff here. So C API, let's just start here and see if we get somewhere. Ooh, so much stuff. This is a funny function. TF get buffer, which just dereferences the pointer that you pass to it. Anyhow, yeah, so apart from all these references to the word tensor, where else do we use the word tensor in this code base? Okay, so this is what I'm looking for, TensorFlow tensor. Yeah, it looks like we're not really using this anywhere here. Or maybe it's just this that I'm looking for. So how can you convert a TensorFlow tensor to a pointer? Or is it already a pointer, I wonder? I wonder if that might be the case. What type is C-tensor? Like, what does that refer to? Let's see if we can figure that out. C TensorFlow, C make lists, okay, C TensorFlow.h, include TensorFlow C CAPI.h, okay. So we're including this file over here. And TF tensor. Oh, where did we import that from? TF tensor.h. So if I go into here, we should be able to see the definition. Wait, what? Okay, so the format for TF string tensors, well, I don't care about string tensors because that's not a thing that we need to even care about right now. This this syntax over here, that's interesting. Does that just mean that it's equal to a byte? I've not seen that syntax before. Let's see what... Or is this just being declared here and it's actually defined in a C file? Let's see. TF tensor. Where are we? This is just an empty struct is what you're saying. Okay, so this is an empty structure. This is an empty structure. How do we create it then? Tensor interface. Okay, yeah, this is convoluted. See, this is why we don't look at the internals of the TensorFlow codebase. Yeah, no, this is just installing instructions. It's ironic how it's easier to get a pointer to a PyTorch tensor than it is a Swift tensor. Really very ironic. But still, it's definitely possible. So as long as I can get the tensor handle, then I can get the C tensor handle, and the C tensor handle should contain... Oh yeah, well, that's not defined in Swift, is it? That's defined in C. So let's just go ahead and print that out. So print pyt.tensor dot, and how do we get the tensor handle exactly? So if we go into tensor, we can dot handle. Let's just do that and see what we get. Okay, so we get the handle, which contains another handle. Oh, no. Oh, that's internal. Come on, did it have to be internal? That's actually not good. Okay. Maybe we could just do C tensor handle? Please work. Ooh, okay. Oh! Interesting. So it's returning a pointer. But I don't know what it's a pointer to. So, I guess we're gonna figure it out then. So, what exactly could this be pointing to, I wonder? Well, I know it's pointing to a C tensor handle, but what is a C tensor handle? Can we figure that out here? Is there no reference to tensor handle in this code base at all? No, there is. There is. But I don't see it in the C API, though. That shouldn't really matter, as long as I can figure out what a tensor handle is supposed to do. Okay, so tensor handle is actually a class. So you can get an eager tensor handle, that's possible. If I were to find the symbols of these functions, I could probably understand them better. So this is a lot of exploratory work to figure out exactly how we can call these functions. Maybe there's more information in the actual header file. It would be a pain to actually manually calculate the offset for any one of these values, if there are any values within this class, but let's see. Okay, so these are private. These don't really matter anyway, because I can't... Oh, well, I could technically access them, but it's just going to be a little bit more... It's just going to be a little bit more annoying to work with and unsafe because it can change. Let's see if there's anything. Get pointer to TensorFlow tensor. Oh, wow, yeah, that's way more complex than PyTorch. Oh, wow. Why? Okay, so there's a tensor buffer that we can use. So internally, this is going to create a tensor buffer. I wonder if tensor buffer is referred to anywhere here. Okay, now we're talking. But this is an internal class, though. I probably can't even access this. If I were to manually clone this API and convert this to a public class so that I can access it and then recompile, I probably could make it work. Let's see, so TF tensor data. Oh, okay. So the TF tensor data function will give you a pointer, but you need to have a C tensor object, I'm gonna call it, for lack of a better word, because I don't know what it really is. How do you get a C tensor then? Because we're referring it a lot of times, how do we actually get one from a regular tensor? Yeah, sure, I can get a C tensor handle, but where do I get the actual C tensor? Okay, so that's not particularly helpful. Okay, so if we go back into C TensorFlow is basically just a stub. Yeah, anything we need for this is going to be in core. Nothing would be anywhere else. Let's see if execution has anything interesting. No, it doesn't. Maybe regular tensor helps us. Okay, so if we get the raw tensor handle, which is basically the same as doing what we just did, but it's still some progress. Okay, so we're getting the same pointer, and that's fine. What would be interesting would be if we could understand how exactly we can convert that tensor handle to a C tensor. Okay, there we go. Now we're getting somewhere. A tensor referenced by a tensor handle may be on any device, whereas a tensor always resides in the host's CPU memory. So the reason we have this whole weird issue is because TensorFlow's wrapping us in a tensor handle, but we want to go back to a regular tensor because we know for a fact that it's on CPU, right? We're making that assumption, but TensorFlow's not letting us make that assumption. Let's see if we can find some sort of documentation on how to handle that situation. Tensor handle to tensor. Oh, Swift docs. Okay, so the make host copy function will only ever make a copy if the internal data is on an accelerator. And since we're making the assumption that it's on an accelerator, we can also make the assumption that a copy will never happen. And therefore, it won't really affect performance that much, even if we were to call the make host copy function. So that's actually what I'm going to do. I am going to make it so that we can take a host copy, and then the shaped array should be a lot easier to convert to a pointer. Let's try doing that. And then to ensure that both the tensor and the shaped array are pointing to the same data, I'll change the values that I see in the pointer and see if it changes the Swift tensor. Let's see if that works. So now we have the slightly less difficult job of figuring out how to convert a shaped array to a pointer, which is pretty easy, actually. Or at least should be pretty easy. Yeah, so with Unsaved buffer pointer literally just does that for us. Okay. So in theory, we should be able to do tensor dot make host copy dot with unsafe buffer pointer 0. Oh, really? Come on. Do we have to get the handle? Oh, come on. Really? Internal? Why is that an internal function? Why would that be an internal function? Come on. Why are they making this so difficult? Okay, so if I just call dot array, which is yet another layer of abstraction, it should work though, which it is. And then just to confirm that we are getting a pointer to the same block of memory that's backing the tensor, what I will do, and hopefully this works, is just do this and then pointer dot base address dot pointy equals 12, and then we're going to print out the tensor. It's probably some sort of syntax area. Yeah, we gotta unwrap. Oh, really? Is pointy a get-only property? It can't be a get-only property. How would you modify a pointer value? Oh, is this a with unsafe mutable buffer pointer? Okay, so now, there we go, finally. So now we can get a pointer to a TensorFlow tensor, and in case you didn't notice, here's what is just absolutely so amazing. In theory, the Swift tensor and the Python tensor should both be backed by the same memory. So when we modify the Swift for TensorFlow pointer, watch this. If this works, I'll be super, super excited. Oh, no, it doesn't. That means there's a copy being made somewhere. That is definitely bad for performance. We don't want a copy to be made. Because when we've got a, like large, say, 256 filters, 64 examples, 28 by 28 image, that's a lot of data that's going to be copied to and from. And so we don't want to make that copy. How would we force TensorFlow to not make that copy, though? That's the question that we have. The initializer that I was using before evidently is making a copy, but we don't want that. Is there a way to do that, I wonder? Will this one not make a copy? No, this will make a copy still. Maybe we could figure out what to do for that within Tensor handle. Because just out of sheer curiosity, I am going to print out the handle. Does that make sense? Yeah. Tensor handle. Dot C tensor handle. I think that's what it's called. Let's see if that is. Yeah, it is. Okay. Yeah, never mind. I had a bit of a misconception, but that evidently is not the case. Okay. See, when we go ahead and actually create this tensor handle and we pass it even like a pointer, it allocates new memory and it copies that tensor data over to new memory. What we want to do is we want to prevent it as much as possible from actually making that copy. We want it to be backed by the same pointer that we were using before. Oh, so we could actually call TF allocate tensor, and well, no, we could make it as if that was called. So what I could do is I could actually clone this repo and add another initializer that just takes a pointer, basically. Should I do that? So the buffer initializer closure is going to take a raw pointer, and what's it going to do? The buffer initializer will take that pointer and put the relevant data into that pointer, as far as I can tell. And so, yeah, that should be what happens. And yeah, that should work, actually. I should be able to trick it into thinking that that's a tensor. I wonder if that's possible. Let's actually go ahead and try it out, shall we? What's the worst that could happen? Although I must admit, I'm not particularly excited about cloning this entire repository, but let's go ahead and do it anyway. So I'm going to go ahead and clone Swift APIs. And if we take a look at the package, is that not a thing here? How, oh, no. Oh, okay, I'm in the Swift directory. Alright, if we take a look at their package.swift file, they have 2 library targets. That's good. Right, that I like. Let's see what their compile instructions are, if they have any compile instructions. So okay, let's try just building. Just whatever's already here, let's try building it. I wonder if Swift alone is enough to compile this, because if we have to install Bazel, then we'll skip ahead to the part where we do the GANs. You can actually hear, as Swift is using a bunch of threads to compile, the fans spinning up. Okay, so it did compile. Oops, debug. And we get 2 shared libraries. Nice. Okay, so now let's go ahead and actually use this new source code that we have to do some fun stuff. So I'm going to go into TensorFlow, specifically into core, and I'm going to modify tensor handle. And what I will do is I will add another initializer that will basically, and just so we don't actually end up messing up something else that actually uses the existing initializer, I'm going to create a new one. So I don't need to call it inlineable, I can just create another initializer, and I will make this one public. So public init. Is this even a public, like, struct? Oh, it is. Oh, yeah, of course it is. It's a tensor handle. Yeah, so I can just do public init shape is an array of integers, byte count, and buffer unsafe immutable raw buffer. And I can just pass it the data directly. Could that happen though? So once we allocate a tensor, it's easy to get the pointer, but I'm not sure if we could just convert the pointer to the tensor in the first place. That is the secret sauce. That's what we need to figure out. TF tensor data will take a C tensor and it will give us the address of the contiguous block of memory that will actually store the data. Allocate tensor will allocate the entire tensor, and I'm assuming that would be a class with a bunch of other stuff in it as well. Is there a way you can get a size of a buffer? Just, I don't think you can. That would not make much sense, but yeah, see, of course. Oh wait, no, never mind. You actually can do that. Yeah, no, this is not something that we want to use because alignment and stuff can actually make it return more. For us to make TensorFlow treat a buffer as a tensor, what exactly would it take is now what I'm wondering. When we allocate a tensor, can we could I just allocate a really small tensor and then manually go in there and change the size and make it point to something else? I feel like that is a possibility. Let's see what the tf_allocate tensor function is. How is that implemented? So they're using the allocate tensor function. This is a lot of functions for something that shouldn't require these many functions. Oh wow, they have their own memory allocator. They're not just using malloc. Isn't that fun? Definitely not fun. Let's go back to tf_tensor.h. Because I want to see what's contained within the struct. Okay. So it looks to me like tf_tensor is it's just a blank structure. Okay, so tf_tensor data will return a pointer to the underlying data buffer. Can I get the pointer to that pointer? How do they implement new tensor? Okay, so they do at least use the original memcopy function from the standard library. Create tensor. Okay, so a tensor only contains a tensor interface. Now, what's a tensor interface? Really, it's as if they couldn't make it complex enough. I wonder if this is a file. No, it's not. We'll search for it manually. Where do they... Oh, there it is. Someone's asking which distro of Linux I'm running. I am running Ubuntu, which is a flavor of Debian, so not CentOS. I prefer Debian-based Linux distributions. Okay. In theory, a tensor what were we looking at before? The previous file. Okay, so a TF tensor should only contain a tensor interface. A tensor interface should only contain a tensor. Okay, so we've gone 2 levels deep. 1 more level to go. So now how exactly do they define a tensor? Now the thing is, tensor is such a broad word, it's going to be used everywhere, see? Yeah, how exactly will we find? This is just a complete guess. Yeah, now it's throwing Java code at us. We don't want that. Now, if only GitHub's declaration searching actually worked on this code base, that would be incredible. Maybe there's a way to construct tensor from pointer TensorFlow. Okay. Now we're kind of getting somewhere. If we have a TensorFlow C tensor, there is a tensor data function, apparently. I'm not exactly sure of whether or not that's the case, but no, but that gives us a pointer. We want to construct. Yeah, shallow tensor would solve all these problems, and there's an issue tracking this, and it seems to be close, so maybe they came to a solution. Okay, it looks like there is a comment here with a bunch of okay, so if we were to create a little fake allocator, that would be fun. But how would we pass that allocator to TensorFlow, though? See, that's the problem. They don't really have much documentation, do we? Pointer to TensorFlow. Oh, okay, there we go. Yeah, see, they're pretty much saying we lack documentation. Oh, this is interesting. You can allocate a tensor and get a pointer to the memory for that tensor. Okay, so one problem has been solved, at the very least. Alright, so we have solved one problem, and I'm just going to save the link to this issue because I'm sure it's going to be really useful. Okay, so this problem's been solved. By the way, the issue that we're facing right now, just I see there are a couple of questions about that, is not a Swift problem. It's more a C problem. So it's more of a TensorFlow framework problem than it is anything else. Like, you saw how easy it was to get pointers in PyTorch. You literally just call TensorFlow.data pointer. But within TensorFlow, you've got to go from structure to class to structure. You've got to do all this weird finagling with the TensorFlow framework to get it to give you a pointer, because TensorFlow really values being able to run on all sorts of different devices, from CPUs to GPUs to TPUs, all sorts of things. And that is particularly annoying. Oh, this is interesting. The underlying pointer can be accessed. Okay, so it looks like half of the problem's been solved because now we can get pointers to TensorFlow tensors, but we cannot force TensorFlow to use a pointer which has already been allocated. So we have a contiguous block of memory, it contains the data that we need, and we want TensorFlow to use that data without complaining, which not particularly easy. Because as you can imagine, if we've got like 256 by even 7 by 7, right, and we've got like 128 examples, and each value is 32 bits large, right? That's not a lot, but that's 6 megabytes of data that we've got to copy over, which again is not too bad. So I feel like let's go ahead and continue using this technique for now, although in the near future it's something that I'm going to take a look into optimizing by creating an issue on the TensorFlow GitHub. So for now, let's just go ahead and assume that we've got to make a copy, right? That's just going to happen. There's no way to get around it. TensorFlow is stubborn. It needs a copy of the data. But then from there, if we have a TensorFlow tensor, how do we convert that to a PyTorch tensor? Luckily, that's probably not too difficult. What I think I should do is I should create a little bit of C code which takes a pointer to a C tensor handle and then does the rest of the operations in C, or C++. But then importing the C++ code for TensorFlow is a bit of an issue, and I don't think we can actually finish that within the 10 minutes that we have left for today's live stream. And so here's what we're going to do. We will continue this next week, or what I will do is I will take the rest of this the rest of the content for finishing up the interoperability layer and the DiffAugment stuff. And what I'm going to do is I am going to go ahead and wrap this up into a single sort of a GitHub repository and then create a recorded tutorial so that we can move on to another topic next week in live coding. Until then, though, what I will do is quickly show you a little bit more of the actual API around DiffAugment before we end today. I'll answer a few questions. So if you have any questions around what we just did or anything else, feel free to put those in the live stream right now as well. Or in the live chat, rather. So what I'm going to quickly do really over here is show you. There we go. Okay, so basically the way this DiffAugment function, the way these DiffAugment functions work is actually quite simple. All you need to do is when your generator generates some images, you pass it to something called the transform function. The transform functions within this is within the what's it called again? It's called the DiffAugment sort of code base. Within the DiffAugment codebase, you've got that transform function. You want to pass whatever you've generated to transform. It's going to, in a differentiable manner, transform them into a bunch of different kinds of images that you then feed into your discriminator and then use your objective function to optimize. Same thing for the real images. You also want to transform those because that way you're getting a lot more data even though you technically only have the same amount of it. And so what I'm going to do is I'm going to go ahead and finish up this whole PyTorch interoperability, implement that in Swift for TensorFlow, and there will be a tutorial soon on my YouTube channel regarding how you can implement that. Alright, so now in the meanwhile, what I also want to do is go ahead and answer any questions that you have. So let's go ahead and see. One question that I'm getting right now is there are actually two people asking the same question. What knowledge is needed to be a tech developer? What are your suggestions regarding that? Well, so more generally what I would recommend, and this is something that you would notice if you actually watch the rest of the live coding series, and as you know, my sort of favorite languages to code in would be languages like Swift or C or Python, whereas there are languages like Go, which up until a little while ago, I didn't really know the syntax for and wasn't really aware of. But in the past few live streams, we've still been implementing a lot of different functionality within the Go language. The reason for that is because while I don't know the intricacies of Go itself, the basics are the same, right? You've still got the same basic programming concepts. And so I feel like really being able to generalize what you learn in the sense that what you learn isn't specific to a programming language or a framework, but more generally your understanding that sort of computational thinking is really important. And so in terms of what knowledge you should have to be a tech developer, it's really just practice of programming or implementing different algorithms or solutions to problems in different programming languages, giving you a good idea for just generally what the world of development and programming is like. That way, you can generalize to different programming languages or frameworks or architectures or whatever else it is. And so, not being specific is definitely is definitely very helpful. Being able to generalize is very important. Also, another question, Tanmay, did you receive Apple's DTK? No, I did not sign up for the developer transition kit program because I do not have currently applications running on x86 that would be important to have ARM hardware to transition with. Although if I did, I would be using a developer transition kit. Another question, which language should we start coding for Android? Swift. Well, really you can use a variety of different languages for coding in Android. There are multiple different frameworks or languages that you can use. Java is the classic one, and unlike iOS, it's a lot less restricted. Although I would say that for modern Android development, do not use Java. Either use Kotlin or use Swift. Right? Swift is cross-platform. It even runs on Windows now, but Kotlin is definitely sort of right after Java. And then if you really want to be modern about it, you're going to use Swift. Another question I see, can machine learning be used to diagnose hearing conditions of a patient? Well, yes. In fact, I have an entire YouTube video on using machine learning technology for audiology. After the stream, I'll go ahead and put the link to that in the description, so that you can check that video out, or you can search up Tanmay audiology and you'll find that tutorial. It's all about using the database available from University of California, Irvine, I believe, in order to train a neural network to identify hearing disorders. All right. So let me know if you do have any more questions, and all right, I believe that is all. So here's the plan. What I'm going to do is I'm going to go ahead and finish up two things. First of all, as I mentioned, the PyTorch Swift interoperability. I'm going to work with the TensorFlow teams to figure out how you can pass TensorFlow pointers and get pointers from TensorFlow, because there's a very specific way in which TensorFlow tensors need to have their memory aligned within memory. And so I'm going to go ahead and figure out what that alignment is about, how TensorFlow expects us to pass it and get tensors from it. Then I'm going to go ahead and implement that in Swift for TensorFlow, and very soon there will be a tutorial on my channel around DiffAugment once more. And next week, either we'll continue with the same topic, or we will be moving on to a brand new topic. And next week's going to be really exciting, more than likely around distributing your applications across multiple machines. It should be a really fun episode. And once again, if you do enjoy this series and you're looking forward to watching the next one, again, we hold this every Wednesday in the morning Eastern time. Please do make sure to subscribe to the channel and turn on notifications. That way you're actually notified whenever I release new content. Once again, thank you very much, everybody, for joining in today. If there are any questions I didn't get to right now, feel free to put them in the comments, and I'll definitely get back to them. Yeah, once again, thank you for joining in, and I will see you next week. Goodbye.